That's homework. Okay, while people are coming in, let me pull up our video for the day, which is one that we took. We took ourselves. This video, since we're going to talk more about electrochemistry, this is something that we work on in our lab, which are called Electrochromic Materials. We have gotten some industry support from Scott Goggles, the snowboard goggle manufacturer, and we're actually trying to develop some awesome goggles that can change tint in real time. So here's our kludgy video that I put together, complete with a vice grip, so you know it's actual science. All right. So there's our electrochromic material. It's see-through when it's unconnected. You can see right through it. What I've built here is a feedback system. So there's a feedback loop. So you've got the electrochromic material that I'm going to apply a voltage to make it change color. I have LabVIEW running. LabVIEW in real time basically allows me to input a desired transparency. It's not strictly transparency, that's harder to measure. Instead, inside of there's a little photodiode, and that photodiode is going to read a value between 0 and 100, right? And so I can set what I want that diode to read. And if I set it down to 40, that's lower than what the room is currently giving it, so that cell turns on, and within about 30 seconds, faster, even this one changed really quickly, you get this real-time control. And when it gets to the diode reading 40, then it'll go back over to that, and you'll see this starts now pulsing, so that green light's flickering on and off. So it doesn't have to deliver current constantly. At that point, it can just pulse, right? And it's going to reach some state. This works because of electrochromic materials work because of electrochemistry. You have to understand how applying a voltage to something causes a reversible redox reaction, reduction oxidation reaction, and that'll be the subject of today. Rob?
Is that similar? They have really fancy adjusted welding elements?
That's exactly what that is. Yeah, they have them in airplanes. They have them in really fancy office buildings on the outside. So how our technology is different than the stuff that's established is that the established stuff they put on with a high vacuum process, which is very expensive. They do big paintings of it. It's very, very expensive because you have to pump vacuum down on it. And what we're making is a thin film like you saw that I could glue to the outside of your window in your car or your home or whatever, and it could be a retrofit. So we're aiming at the retrofit market. If you don't want to spend $10,000 or $15,000 to get new windows on your home to make it more energy efficient, what if you could just put an electrochromic material that would absorb IR radiation and prevent that from getting in your home? That's the goal of our market.
How do you have to apply voltage to that electricity?
Great question. We won't cover it in this class, but if you take, like in the electrical engineering department, Manon has a class on optics, energy optics. He'll talk about light sensitive, that's photochromic. Okay. So if you've seen glasses that change on their own, those are photochromic. This is an electrochromic material, meaning you have to apply a current to get it to a voltage across it. Okay, so there is a second homework. I will post it after class today. Homework 1's getting turned in, so get that in. We will do clickers today. So for your clickers, if you have a physical device, one of these things, you need to turn it to receiver channel 41. And if you're using ResponseWare, which I hope you guys are, save the money, then you go over to it and you put this number in, 174670. And I will actually start this, and you'll see those numbers still when I start it. Okay, so that's channel 41, that's your session ID, so that info should be there. Okay, today, let me start off with our learning objectives. Our learning objectives are to learn how to use a standard reduction table to predict which metal will be oxidized and which one will be reduced when we put them together in a galvanic cell, right? We're then going to predict the voltage of that galvanic cell, and we'll do so as a function of the salt concentrations of those two ions and as a function of temperature. Finally, if we have time, we're going to talk about oxidation rates, which is not the same as like a redox reaction between two different metals. This time oxygen's involved, and we'll use a formula known as the Pilling-Bedworth ratio to give some additional insight. So picking up where we left off last class, let me clarify and correct a few things I said. First off, about partial pressure. Partial pressure has the units of pressure. So the partial pressure technically has units of pressure, meaning right here, if you take the fractional composition and multiply it by the total pressure, you get the partial pressure. And there are some great examples you can see where they do that, right? Where they basically go through that process. So that's all linked now in the notes here. The pressure, however, should be in specific units. It should be in either bars or ATMs, right? You can't do it in pascals and get the same answer, right? It needs to be in bars. Technically, an ATM is almost the same as a bar, so ATM in this class is fine. So if I ask you what the partial pressure is for these reactions where we're looking at free energy, it would be PA, where PA is the fraction of the moles of component A times the total pressure. That would give us the partial pressure. So thanks, I think it was Jimmy that caught me on that one. Jimmy? So appreciate that. Then next off, I said that if the reaction quotient is 1, and we said reaction quotient was 1 in this example up here. We said if this is a solid, that's a solid, and your chamber is completely filled with carbon dioxide, we said what will happen? Well, we said Q must equal 1 over 1 multiplied by this partial pressure of CO2. And if that's just 1, then Q, our reaction quotient, equals 1. Therefore, in our delta G expression, we have RT natural log of 1. That means this whole term right here went to 0. Right? And so I said the reaction doesn't go forward. That is strictly speaking from the experimental standpoint, right? We know that the total thing that determines whether a reaction goes forward is delta RG, right? Which has both a theoretical component and an experimental component. So I was wrong to state that it doesn't go forward because it could go forward based on the theory, right? So we're going to do lots of examples of this because I think there's a little bit of confusion in the air. So we have today, and I'm also going to spend, I think, an extra lecture on this on Friday. So we'll do lots of examples of free energy and electrochemistry where we actually calculate these things. So that's correction from last time. Again, from the experimental part, it would definitely be 0. But the theoretical part could still dominate to make the reaction go forward or backwards. So let's start with this one. We left off last time with this reaction, the sodium NaHCO3, can't remember the name of that, and then NaOH and CO2, right? That's our reaction, and we're going to assume that we start out with excess CO2, that the chamber is basically filled with CO2 gas. So the reaction is going to reach equilibrium when delta Rg equals 0. Delta Rg, I'll remind you, is this one on the left, right? That's the one that takes into account both theory and experiment. When that equals 0, there's no reaction going forward or backwards, which is really to say that there's the same amount going forward as there is going backwards, right? So that is the definition of equilibrium, when delta Rg equals 0. So it would be a fair question to ask, what will be the final pressure of CO2 at equilibrium? So to solve this problem, you're going to say that delta Rg must equal 0 because it's at equilibrium, and that still equals delta Rg naught plus RT natural log of Q. Okay? And you remember that Q in this case just equals the partial pressure of CO2. Okay? So if I've given you this information, we can answer this question. What do we have to do to answer this question? Actually, this might be a clicker question. So I'm going to start the clicker up here, and I'm going to get this out of the way because it's harder to read. Basically, it gives you two options, A or B. Is the answer negative 77 or positive 77? And let's work through it together on this first one. So what's the first step to answering this question and figuring out what will be the partial pressure? Or actually, I guess the question asks, this one asks what will be delta G formation. So let me pull this back up. It says, if delta G formation at room temperature for these things are these three values given there, what is delta Rg naught? So what is the change in free energy naught? Meaning, what is, sorry, let me pull it up, where'd it go? Lost it. What is this value? So the first part of the question asks what that is. Okay? How do we solve that based off of this information that I've given you here? On the clicker, I actually made it easier. I told you what NaHCO3's value is. It's right here. Here, I haven't told you that, but I've given you this information. So how do we set this problem up? Anybody want to take a stab at it? Or at least tell us what to do next? Or how about this? Tell your neighbor what you think you should do next. Okay, so let me pick on Polly. What do you think? How could we start this?
Using the equation that we have for delta G in our notes.
So G equals, H minus TS, right?
Yeah.
So I've given you H and S, and we know that since this is F naught, that's happening at 298 Kelvin, right?
Yeah, so then use that to calculate for the sodium carbonate.
Yeah, so we'd say negative 950.8 kilojoules per mole minus, minus 298 Kelvin times, now watch the units here, this is tricky. The first one was in kilojoules per mole, this one's in joules per mole, so turn that into kilojoules to save yourself the headache. 0.102 kilojoules, and that's per Kelvin mole, right? So when we do that, our Kelvins cancel, right? And we're gonna get an answer in kilojoules per mole, okay? Which is what we want, right? So somebody give me that value, and let's hope that it's the same as, where'd this thing go? Let's hope it's negative 851. Okay, somebody have that yet? Huh, something's wrong. It should become more negative. What if I've got a wrong value here? Let's use the value in this one just so you can do the clicker question right. Let's assume that it comes up to negative 851, and by next class I'll figure out what the problem was there. I probably just typed something out wrong. So that's the approach though. Any questions on the approach at least, that you do G minus HTS? Right, G equals H minus TS. So let's assume that it's negative 851. What is happening? Negative 851 kilojoules per mole. Now that we have that for an individual compound, how do we figure out delta RG naught, which is what this question is asking for? Yeah, it's going to be products minus reactants. So in this case, our products are the NaOH and the CO2. Right, so delta RG naught will be equal to negative 379.484 plus negative 394.35. That value minus this negative 851. Okay? So we plug that in. Which one is it? We say, in fact, let's just do this. So I'll start the clicker question now. You can actually be putting the answers in right now, I think. So you should be able to enter A or B. Let me get this out of the way for you. If you don't have a calculator, lean over and work with a friend. That's fine in class. Yeah. Probably that number up top there, that 174670. That's If you've registered it, then you're so in class, you can check. I'll post it. You can make sure that you Okay, another 2 minutes. Get that answer in. That's a very maybe 1 minute. Like you should probably have this by now. In fact, is anybody still working on it? Can we move on? Okay, I'm gonna hit next. So this one, wherever my button went. So we stopped this one, and yeah, the great majority of you guys got that it was a positive 77. So if you got it wrong, make sure that you were actually doing products minus reactants. Okay. So that said, the next question is this reaction as it's written spontaneous? Okay, 30 seconds, get your answers in. Okay, gonna end the poll. And people think that, yeah, this is not spontaneous because delta G was positive. If delta G was negative, it would be spontaneous. So that said, what will happen to this? Well, too many things open. It means it's going to go backwards, right? Instead of spontaneously forming more CO2 gas, since the chamber was full of CO2 gas when we started, it's actually going to start going backwards. Some of that CO2 gas and this NaOH are going to react to form some of what we had written as our reactants. Some of those products are going to go back to being reactants, right? So the question then is, what will be the final pressure? Well, now we can finish this question, right? So now that we know what delta RG is, and we've set this equal to 0, all you do is you plug in the temperature this is happening at. We're going to say room temperature, I think, on this one, room temperature, and you just solve for PCO2, which is just equal to Q. So go ahead and do that. Solve what this would be. Right? What is R equal to? R is the gas constant. You'll remember from chemistry is 8.3144 joules per mole. Per mole Kelvin? Per mole Kelvin, right? It's got to be. Yeah, it is. Joules per mole Kelvin. Okay? So if you plug in room temperature, 298 K, you should be able to solve for the partial pressure. Let's give ourselves a little more room. Remember that this is in kilojoules. Let me go to the next question. Okay, and the next question is asking for this. So which one of these is our answer? What will be the final partial pressure of CO2? Which window is valuable? Here? Okay. Okay, so get your answers in. We'll do 2 minutes on this. Good.
8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31. 8.31.
The question is asking what will be the partial pressure of CO2 at equilibrium. So it's this equation right here. You're just finishing the calculation on it.
So it's
One thing to watch for is that this is in kilojoules, and R right now is written in joules. Okay, one more minute. Okay, get your final answers in. Looks like most people responded. Okay, I'm going to end the poll. A or B. People think it is what? People think it's A, right? So that's good. So this, any questions on this type of problem? Yeah, Kylie.
I think I only have questions actually. Like I don't think I have anything.
Should I recap the whole thing? Let me recap the whole thing, okay?
You actually calculated it out.
Can I calculate it out? Sure. So PCO2 is going to be equal to exponent of -77. Let's write this in joules. 200. That's joules per mole. Divided by 298K times 8.3144 joules per mole K. Right? That gives us, by my calculation, I left off at 2. Let me just add it real quick. Yeah, I get 3.18 e to the negative 14. So roughly 3 to the negative 14. Okay.
So how do we factor in the concentration of the sodium hydroxide?
How do we factor in the concentration of the sodium hydroxide? So in this case, why could we write Q as just the partial pressure of CO2? Because if you look at our reaction, the only gas that's present is the CO2. These are both solids. If those were gases, then we need to know what their values were to solve this question.
We'd also consider if they're aqueous, right?
If they were aqueous, then you have to deal with their concentration. We'll talk about that later today when we talk about batteries. Okay, so let's recap this question. This whole concept. We introduced free energy. Free energy takes into account both enthalpy and entropy. Since those both matter, we need them both. Free energy is G. And then free energy itself has two components. If we're looking at a reaction, we want to know what delta RG is. That says, does it go forward or does it go backwards, right? At equilibrium, it's equal to 0. If it's positive, it goes backwards. Forward, it goes negative. Or negative, it goes forward. But delta RG itself depends on both the equation as it's written on paper. We'll call it the theory value. That doesn't know anything about what's in the chamber where the reaction's actually happening. And then there's the experimental value. And that doesn't care what the theory value is. It just says reactants versus products. How much of these are there right? What's that value, okay? So delta RG needs both of those factors. In this question, I gave you the reaction as written on paper. So as it's written on paper, you'd be able to figure out delta RG naught. That's the theory value at room temperature as it's written on paper. To do that, you need to know delta G F naught values for all the compounds. I gave it to you for 2 of them, and for the third one, I gave you H and S so we could calculate it. Okay? Now we know delta G naught, delta RG naught, which is, does the reaction happen according to theory, knowing nothing about what's in the chamber? Then we had to take into account experiment. There, I told you to start with that the reaction chamber was full of CO2. And since that's the only gas that's present, our reaction quotient was just Q equals partial pressure of CO2, because the solids are just equal to 1. Since we know that, we can say RT natural log Q, we can figure out whether from an experimental perspective this one goes forward, right? And we found out that it doesn't. So when we plug in everything, we find out that the overall delta GR for this reaction was positive, meaning it goes in reverse. So then the question was, how far in reverse? When will it stop going in reverse? To answer that question, we had to set delta RG to 0. That's the equilibrium position, right? That's the definition for equilibrium. And when we do that, I just brought this delta RG naught, which doesn't change from before, to the other side of the equation, and we ended up with that negative 77 this time, equals RT natural log of Q, which is just partial pressure of CO2. Solving for partial pressure of CO2. Any questions left on that? Sophia? Wait, Sophia?
Yeah. Well, I told us that at room temperature again.
Room temperature, by definition, you can use 300 Kelvin, but the actual value that everyone uses in chemistry is 298 Kelvin.
For what in the problem told us is at room temperature?
Sorry, which one is at room temperature?
Like, how did we know to use room temperature?
I don't know what's that.
I would have had to say in the question at room temperature. So I just told you guys, on a test question, I'll say this is happening at room temperature.
Okay.
Yeah, for sure. Good point. Shannon?
Yeah. What's the units on the answer that we found?
What are the units? Okay, great question. So up here in my clarification from last class, we said that when you do pressure in these reaction quotients, it needs to be technically in bars, but ATM is almost the same thing as bars. So that would have the units of bars technically, but ATM is fine. Right? So basically, it's going to be a very, very small number. Okay. Yeah.
Since you gave us the delta H and delta S as standard temperature and pressure, can't we assume that it's 298 K because it's standard temperature and pressure?
Can we assume that it's time? Correct. Yeah. Now on the homework, let me pull it up real quick and show you guys what the homework will be. I know. By the way, karma is real. You guys, who stayed up late last night working on the homework? Raise your hands. A lot of you. Karma is real. Karma got me. My 5-year-old came in my room at like 3 in the morning with a bloody nose after having dripped blood throughout the house. So we were all up last night. I got what was coming to me. So homework 2, I'm going to give you an example of delta G naught values, but not just at room temperature, right? I give it to you at room temperature, and I also give it for, these 2 compounds at elevated temperatures, okay? So when you do something at elevated temperatures, a reaction, let's say the one that we just did, this salt, right, the sodium NaHCO3, if you were going to recalculate this and say, does it still happen at 1,000 degrees Kelvin? You can't simply change out 1,000 Kelvin right here in the temperature. You would also have to modify your delta RG not to be not just at room temperature, but now at 1,000 K. So I'd have to give you values like these at 1,000 K to figure that out. And you'll have an example to do that on this homework. Okay. Any questions left on this? Kylie?
So just quick conceptually. So delta RG is the free energy that tells you what direction it goes, right?
That's the change in free energy for the reaction as written. And if the energy goes down, we know that the whole universe, if it's spontaneous, it wants to go down in energy, it wants to lower its energy. So if that value, the change in energy is negative, then it went down in energy. And that's why it happens as written. If it's a positive value, that means for that reaction to go forward as written, it's got to go up in energy. So it won't happen. It's going to go backwards.
Okay, so then the change in free energy for formation basically tells like how much energy is needed or how much you're released from this form.
If you were to only consider as it's written on paper, ignoring how much of the different quantities are available.
Okay, and so that's just what the second part accommodates for the error you have in your calculation.
Not error necessarily, that's maybe not the right way to phrase it, but it takes into account real world conditions. What's in the crucible or the beaker or the test tube where this is actually happening at. On paper, it's fine to say that gasoline joins with oxygen, it combusts and forms CO2 and H2O. But if you have no gasoline to start with, that reaction can't go forward, right? Or if there's no oxygen in the chamber, it can't go forward. That's all that's saying.
Okay, so that's why you use that, because it depends on your temperature and your pressure, essentially, like how realistic your calculation will be. And so that's why you use that to kind of, I want to say like, just fix it basically.
Yeah, I mean, maybe the right way to think of this is like, in chemistry we learn about these reactions, we calculate delta G. But as engineers, we actually use these in real world scenarios, right? So you have to take into account both what's actually happening and what it should be on paper. Okay, any other questions on this? We will do a bunch of more examples. This is very typical of a type of question I'll put on your midterm coming up. Okay? Okay, so chapter 16 officially picks up here. They skipped all that thermodynamic goodness, I don't know why, but they did. Now chapter 16 picks up. You should be responsible for read sections 16.1, 16.2, and 1610 in the 3rd edition book. I imagine it's probably the same in the other editions. There's some of this chapter that we're not going to test you on. Things like the rates of these electrochemical reactions, we're not going to test you on. It's just the basics. So let's talk about electrochemistry. Electrochemistry is an electrochemical reaction that combines both an oxidation and reduction half reactions. We're going to come back to that over and over and over, and that makes our life a lot easier. That it always has one of the oxidation type and one of the reduction. So let's talk about one of the classic examples is zinc metal in an acidic solution. Okay, so you've got 2 beakers. You've got your voltmeter that you're reading across them. You put a piece of zinc in one. You put a salt bridge. A salt bridge is literally, you can use a straw from McDonald's that you pack with like filter paper that is soaked in salt water. We'll talk about why you have to have that in a minute, but it has to be there. And then on this side, you've got hydrogen gas and a piece of platinum wire or something as a catalyst, and you're going to have this reaction taking place. You're going to have zinc metal being dissolved, right? Over time, this zinc piece of metal is going to be shrinking. It'll be disappearing. And on the other side, you'll see little bubbles forming over here in this little beaker thing that they've got drawn here. And that means that hydrogen gas is being evolved, right? So what are the oxidation and reduction reactions? Remember oil rig. Oxidation is loss. Reduction is gain. So tell me which of these two things, the hydrogen or the zinc, is losing electrons?
Zinc.
Zinc, how do we know that zinc is losing electrons? Yeah, it's going from zinc metal over here to zinc 2+. So it's lost 2 electrons, right? So we can write that reaction. This is going to be a half reaction. We're going to say that zinc, zinc, right, goes to zinc 2+ plus 2 electrons. Screen flashing. Sorry for that, I don't know why it's doing that. Okay, zinc goes to zinc 2+ but 2 electrons. This is oxidation. Okay, any questions on that? That's clear? So what is being reduced? The hydrogen. As written right here, we've got 2 H+ molecules, or ions I guess we should say, in solution. That's coming from the acid. We had to put this in acid for that reason, right? Acid dissociates into H+ and whatever the conjugate is for the acid. It's going to pick up, so it's going to, what's wrong here? So there's a problem here. These are both written as reductions, aren't they? Right? So that's not right, right? Because we know that for a redox reaction, we have to have both reduction and oxidation, right? So we need to rewrite this. We need to say, H2.
No. You're doing it right.
Oh, that equation's wrong, isn't it? That equation is wrong. The internet lied to us. We learned a valuable lesson today, everyone. The internet lies to us. That's not right. Let's get rid of that. H+, sorry, that's not 2, that's H+. Say 2 of these, plus 2 electrons goes to H2 gas. That is a reduction. We know it's a reduction because it gains electrons. It started out as an ion, it picked up some electrons, it became H2 gas. That's why it bubbles. So the internet lied to us. I apologize for that. Okay. So when you combine these together, we can add these 2 reactions and we get 2H+ plus zinc metal plus 2 electrons yields zinc ions, zinc 2+, plus hydrogen gas plus 2 electrons. The electrons cancel on both sides, and they should. If they don't, then you haven't balanced it right. The electrons need to cancel out, okay? So that's our reaction. Our reactants are hydrogen ions and zinc metal, and our products are zinc ions and hydrogen gas, okay? Fair enough? That is the basis of what are called reduction tables. They always use this curious setup of flowing hydrogen gas with a platinum electrode at room temperature on one side, and on the other side, they always have some metal sticking into it. And by doing that, they can measure what voltage is produced when this reaction either spontaneously occurs, or if they have to drive it with a voltage, they can measure what that voltage is. And from that, they generate these standard reduction potentials. So by definition, since everything is compared to hydrogen, they make hydrogen values equal to 0, right? They say hydrogen ion picking up electrons to form hydrogen gas, we're going to call that potential 0, right? The only reason they can do that is because they're comparing everything to it, okay? It's the basis for all these comparisons. So these tables, that's always in the middle. Now things above that table, things up here, we're going to say are less reactive. What does that mean? It means that these reactions, as written, are favorable and spontaneous. So spontaneous reactions, as written, okay? And below it, these things are going to be more reactive metals. Or in other words, the reaction is not spontaneous, as written. Reaction not spontaneous.
Question.
Yeah.
If the ones above react easier, so they just react spontaneously.
The metal is less reactive. Like think of the noble gases, and they also call them noble metals, like gold. Does gold tarnish easily? No, it's pretty unreactive, right? Platinum, same thing. Silver, that's why we make jewelry out of them. If you made jewelry out of like sodium, it would turn into sodium oxide like right away. It'd be a bad idea, right? So these are more reactive metals. We're going to talk more about that. That's a fair question. One question that you guys should all be wondering is, wait a minute, the voltage here is positive, and you're saying that a positive voltage is spontaneous as written, and here negative is not spontaneous as written. It's the opposite of delta G. Sorry, I didn't come up with it. You can blame chemists, Faraday or Nernst, whoever came up with this. It's just opposite. I'll come back to that in a minute. Let's go back to do another example, and we'll talk about this more. All right, so we showed you the penny battery last time. A penny battery, you saw that we were able to light up an LED just by stacking stainless steel washer, piece of salt bridge, right? Just filter paper soaked in salt water, and then zinc. And then we did stainless steel, filter paper, zinc. Stainless steel, filter paper, zinc. We stacked up like 6 of these, and then we were able to light up an LED. What was actually happening? What was happening is we just had a controlled redox reaction that produced a spontaneous reaction, and therefore it had a voltage that it just spontaneously created, okay? And that's the voltage we use to light up our LED. So if you were to put copper and zinc into 2 solutions, and in the solution you had copper ions with the copper metal and zinc ions with the zinc metal, right? And you hook these up, you put the salt bridge on, you make them electrically in connection, which one's going to corrode and which one's going to have material ions from the solution build onto it, electroplate onto it, right? Which one will dissolve and which one will precipitate from the solution is the question. Well, we can answer this question, and this is why what you guys are in this class, because you care about dealing with corrosion when you design your bridges and your cars, whatever devices you're making. You would look at your standard reduction potential table, right? And you'd find zinc and you'd find copper. Copper is right here. Copper picking up 2 electrons, copper ions picking up 2 electrons to form copper metal. And then zinc is down here. Zinc, 2 plus ions picking up 2 electrons to form zinc metal, right? So which one is going to do the reaction as shown here, right? That's a fair question. So the one that is, should I say this correctly? Reactions on the top of the reduction temple, so ones that are higher up on this table are spontaneous. So as written, copper 2 plus ions are going to come out of solution and form copper metal. So it's going to plate onto the outside of the copper. And the other one needs to be reversed, which means zinc metal is going to dissolve into a mixture of 2 electrons and 2 zinc 2 plus ions, right? So that's always the case. I can give you a table like this, and I do it on the homework, I'll do it on the first midterm. You'll have a table like this, I'll give you 2 pairs, whichever one's higher up proceeds as written. The other one must be reversed, okay? We'll do an example of this. So let's write it for the copper and zinc. And have you know this is true? So if you put together copper and zinc, we know that zinc is dissolved, right? It states it right here, and copper is precipitated. But if we use iron and copper, now the iron is dissolved and copper precipitated, same as before. But if we use iron and zinc, all of a sudden the zinc is dissolved and iron is precipitated, right? So we can change whether or not iron is dissolved or iron is precipitated. We can make sense of that by looking at our table. Let's look at iron and copper first. Well, where's iron and copper at on this table? Here's iron, right? Iron and copper's above it, which means iron's going to dissolve because it's lower on the table. It's gonna be the one that switches, and iron metal will turn into iron ions, right? But iron versus zinc, all of a sudden iron's higher, so it will actually plate out. It's going to precipitate as opposed to dissolve.
Why are there 2 iron values?
That's an excellent question. Why are there 2 different iron values? Because they're different reactions. In one case, you've got iron 2 plus picking up 2 electrons to form iron metal, and here you've got iron 3 plus ions turning into iron 2 plus ions, and they have different voltage associated with them. Yeah, Rob?
Would you like us to familiarize ourselves with this table, or would you give us some?
I would give you this on the test. In fact, so all my homeworks are just old test questions, and the homework for this week coming up, of course I already closed it, pull it up again. I give you a table like, it was open. It's right here, right? I gave you this, and I asked you to answer questions based off of that. Okay, so any questions on this, Simone?
So if you have like iron 3 plus going to iron 0, are the values additive or?
Are they additive? Let me get back to you. I think the answer is yes, but I don't want to confirm that just yet. I'll have to get back on next class. In general, using these tables are very, very easy. They're called galvanic series is another word for them. In your book, it has like a galvanic series. And it's a very, very useful thing when you're trying to figure out sacrificial anodes. Anybody heard that word before, sacrificial anodes? That phrase? Allie's heard of it. She's the only one, I think. Sacrificial anodes, if you have a water heater, you put a sacrificial anode on it. Why? Because your water heater, if whatever component in it is that's susceptible to corrosion goes bad, you're going to get water flooding in your house, and you don't want that. So whatever that component is, probably a valve somewhere, I don't know what it is, it's probably a valve. You don't want that to corrode, even if you have it connecting to other things or whatever, and it might normally be corroding. So instead, you hook up what's called a sacrificial anode to it, and that will intentionally be corroded instead of the valve until whatever your sacrificial anode is completely gone, and then when it's gone, maybe your valve will start to corrode. But the idea behind these is that you put in something that you know will corrode. So looking at this table, how would I pick a good material for a sacrificial anode? What am I looking for? Yeah. So something higher on the table means that the reaction as written is spontaneous. The reaction as written means you're going from ions and you're plating out, you're precipitating. For our anode, we want it to be the exact opposite. We want our valve, which we don't want to go bad, we want it to plate out, if anything, right? We don't want it to dissolve, because that will cause leaking and ruined carpet or whatever, right? So we want something that will be spontaneous in reverse. We want, for example, zinc metal to spontaneously turn into zinc ions and electrons, right? So you actually pick things lower down as your sacrificial anodes. Can you go too low? Yeah, you betcha. If you put potassium and sodium, these things are extremely reactive. They're going to burn up way too fast, right? Just in air, they're going to react with air actually and oxidize. So that's not going to be valuable for you. So you want to pick things like, I know they use magnesium, I know they use zinc, they probably even use, I bet they don't use aluminum for a reason, I'll talk about why, right? But those are your good candidates for sacrificial anodes. You connect it up preferentially so that that will be the thing that undergoes the oxidation reaction, so that your material that you don't want to corrode has the reduction reaction occurring. Okay? Any questions on this? Yeah, Rob?
So like you're talking about the potassium and the sodium, can you use those as compounds with other stuff, or they have to?
Oh, they use them all the time, sure. Like we use these in our labs. If you use sodium metal, like we work on batteries, and some of the things we work on are sodium, like you're all aware of lithium batteries. We're working on sodium batteries in my lab. And if you're working with sodium metal, you can, but you can't do it in air because it will immediately, if you scrape off the surface, I'm sure we can watch a YouTube video on it, we'll find it for next time. If you scrape the surface off with some sandpaper and just watch it, you'll see a new oxide coat form.
But so in these situations with these experiments, it needs to be a pure metal for this reaction to occur successfully?
As written, these are pure metals. In the real world, we work with alloys. And so the table in your book, you have this table, and like 2 pages later, you have a galvanic series table, which is actual metals that are engineering materials. So aluminum 1100, steel 316, those things are listed in terms of the potential involved when they have reactions, right? So things that are most likely to oxidize are things that are going to be dissolving, okay? So that's the galvanic series. Sorry, this is flickering, I don't know what's going on. Okay, any questions on this? I'm gonna give you a table. Which one gets oxidized? The one that's lower down on the standard reduction potential table. If this was an oxidation potential table, which sometimes people report, that's obnoxious, I'm sorry that's happening. Pounding the table. Then it would be just opposite, right? So let's dig into this a little bit more. Let's write this out. Let's do it for the iron and zinc couple, right? So let's first write out the reduction potentials. We'll say that iron 2+ picks up 2 electrons to form iron metal. Zinc 2+ picks up 2 electrons to form zinc metal. What are the voltages associated with those? The voltages are written right here. They call those V naughts, right? So iron is negative 0.44. Voltage naught equals negative 0.44 volts. Meanwhile, for zinc, the voltage is negative 0.763. V naught equals negative 0.763 volts. So we know that they can't both be reduced. One has to be reduced and one has to be oxidized. And we remember that the one that's lower on the table is the one that gets oxidized. So what do we need to do to the reaction for zinc, since it's the one getting oxidized? What do we have to do to it? Yeah, we flip it. So we're going to scratch this out and say that one's getting oxidized. So let's rewrite it as zinc metal turning into zinc ions plus 2 electrons. Really, really obnoxious. I'm sorry that's happening. It's like not in all the way. Okay. Zinc 2+ plus 2 electrons. Our voltage is now going to be positive 0.763 volts. If you flip the reaction, you flip the sign. Just like with free energy where you had to flip it, same thing here, okay? So when we write the overall reaction, we're going to have zinc metal plus iron ions forming zinc 2+ ions plus iron metal. And the overall, they call it delta V naught, is you just add those 2 voltages up. And in our case, it's going to be positive 0.323. Positive 0.323 volts. Since that voltage is positive, that means that it's spontaneous. Remember, this is the exact opposite of free energy. If it was a negative free energy for the reaction, then it's spontaneous. For voltages, it's positive, and I did not choose that. That is just how it is, right? In the back, was there a question?
Yeah, so are we assuming we're putting like 2 pieces of a piece of zinc and a piece of iron in a mixture of the both?
What you have to have for this to work,
2 different beakers.
yeah, for this to work, what you have to have, they could be in the same beaker, but you have to have the appropriate ions in those beakers, right? So if you know, in our case, it's iron, is that what we're doing here? Iron is going from iron ions to iron metal. So wherever the iron is, you have to have iron ions also present. They can be in the same beaker. So if you look up, I don't know if I can Google it, if they'll have it. I'll show a picture soon. Actually, maybe I have it in the notes. I don't. I did a project for Kennecott. What does Kennecott make? They make a whole lot of copper, right? They mine it out of the ground. They take it from being in an oxide or a carbonate state into a metal state. But that metal has lots of things like bismuth and other stuff in it. So as they refine it, they do an electrodeposition refining process where over here they have a big steel plate that has copper on it because they dipped it into molten copper, right? And then on the other side, they have pure copper, excuse me. They have the molten copper with like the impurities. They make a big sheet of it and they put it in an electrolytic solution. Over here they put a steel plate, and by driving a voltage between those two things, as long as it's a large enough voltage, these copper ions will dissolve into solution and then plate out onto the steel. But the bismuth and the mercury and the things that you don't want in your copper just fall out. If they went to a large enough voltage, they would all plate, but if they control the voltage carefully, they can just get copper. If they do this over and over a few times, all of a sudden you have very, very pure copper. So we'll talk more about that. You'll have homework problems where you're going to do that as well. Any questions on how we got to here? Right? That you add the voltages. It's just like with free energy reactions that you add them together. Okay? Okay, and like I said, there are lots and lots of tables out there. You can look up what would be reactions for different things. This one's really nice because it says for materials that you might actually use, bronze, brass, lead, these different lead alloys. If you pair it up with any of these other things, which is the same things, it tells you whether the metal of the top row gets attacked or the metal of the side row gets attacked. So for example, if you put copper together with stainless steel, it's a red. It's a value, it says 320, that's millivolts, 320 millivolts, and since it's red, we know that's the side row, it's the copper that gets reacted against. When you put steel and copper together, copper is going to be dissolved, right? So, and it actually gives you a value, right? Now these values are approximations because you need to know what the concentrations are, but this is actually a pretty valuable table. So why did it take Emily 6 or so of her zinc and steel washers to light up an LED? Well, let's look at it. She had zinc. Zinc is, where's zinc at? Zinc is down here, right? So here's our row, and what column do we want to compare it to? Well, that's our row. We look up here now for steel. It's probably a stainless steel alloy, right? So maybe this one, I don't know. It says 400 millivolts, and it's the zinc that's being corroded. So for every one of those couples that we put together, this rough table says you should get about 400 millivolts. She had to stack 8 of those, so that's 3.2 volts overall. And what's the voltage on those blue LEDs? Probably something like 3 volts. Yeah, a blue LED usually takes about 3 volts. It's more than a red or a yellow, right? So that's why she had to stack 8 of those things to get it to work. If you stop at 4, you're only at 1.6 volts. You're not there yet. So you've got to keep on stacking these together, okay? So there's great tables. A table like this is a great tool for you to use. It's a very practical, if you graduate from this class, you take this class, you'll at least be able to look at a table like this and say, all right, we have a nickel and we're going to bolt it up to a piece of titanium. What's going to happen, right? Nothing or something. It says the titanium, it's a positive value of 90. It's a very small voltage, which means it's a very small driving force, meaning that reaction is not going to be severe. It will corrode, but probably slowly. Whereas if you took nickel and paired it up with something clear over here, like whatever that is, magnesium, yeah, you betcha, magnesium's toast. Magnesium reacts like crazy, okay? Any questions on this? Okay, we're out of time, so we'll pick up here next time. We'll do one more lecture on this.